Hello everyone. Today the topic of the session is going to be about Laplace transforms, which you might know, you might not know, but it's a very important result in physics. It's used to convert the function from time to frequency, which are two different domains. So this type of expression really is called an integration or kernel in mathematics, and it's just a fancy word for taking a function and changing the input, transforming it into a different domain. So it's useful in wave analysis, and it goes really well together with the convolution integral, which I'll cover in a different video, as well as the Fourier transformation, which I probably won't make a video about, but still it's good to know. So we're just gonna do the maths behind it. We're not gonna do any physics. So the reason why I'm doing it is because I should like to show you how Laplace can be used in second order differential equations. So yeah, that's my motivation here. So okay, let's start with something easy, relatively easy. Okay, we want to find the Laplace transform of t. Yeah, as simple as that. Well, actually, you know what, we'll do that later. Laplace transform of 1, but notably the 1 is in units of time rather than frequency, so just so you don't get confused. So our f of t here is just 1, so it basically means we're just finding the improper integral from 0 to infinity of e to the power of minus st. So that's not much of a big deal. You don't need to use integration by parts or anything. Let's just dig into it. Okay, so then you have integral from 0 to infinity of e to the power of minus st. Okay, dt. Yeah, some people forget the constants. The constants in the end of the integration process, but I also forget it with respect to t sometimes, which is a bit annoying. Anyway, okay. So then we know that s can be treated like a constant here. So then we have this. Well, notably, what I meant here is, yeah, it doesn't make sense. This is just going to be the antiderivative for now. And then what I'm doing is I'm taking this, and I'm going to see how you work out the definite integral of this expression here from 0 to infinity, which, you know, it's not that intuitive. So what we need to do is essentially look at the limit as a approaches infinity of this. Okay, so what do we see here? Well, this is a constant, doesn't change. Well, times e to the power of st and minus st, and t can be usefully thought of as infinity. So in that sense, we can say we have infinity s if you like, but that's not really mathematical. But then you just know that that's infinity, and there's no useful expression for e to the power of minus infinity other than just 0. So then this is just 0. So then, yeah, if this is a product of something times 0, then it's 0 as well. Then, as we often don't do with definite integrals in regular calculus, but as you can do, and gives a valid result, we're gonna use a little sneaky technique here minus it from 0, although it's not really needed in regular calculus. We haven't found the useful result we're looking for here, so that's what I'm going to do. So yeah, we're doing because we're trying to think of this whole expression here minus st as being 0 now, because we're looking at the lower bound here. What we get here is essentially, this expression here, 0 minus 1 divided by s times 1, because minus 0 is 0, and anything to the power of 0 except 0 equals 1. Okay, so then we have, plus reciprocal of s. And that's what we've got here. It's actually really interesting because talking as somebody who just did his physics GCSE, we learn about waves and how to find the frequency of a wave. And it kind of does show this relationship between frequency and time, because you're looking at how much a certain wave has occurred in a given amount of time, because that is frequency. So it makes sense that there would be like an inverse relationship between them. But anyway, okay, that's one done. Pretty easy, but yeah. I'm going to do the Laplace transform of sine of at, with a just being any number really, but finding the Laplace transform of sine of t is quite long, so you might as well just do a as well, with the consideration that we have a limited amount of time. Anyway, okay, Laplace transform of t. What we need to do is essentially do exactly what we did here for improper integrals, but the thing is here, we get and this is a product, so we have to use integration by parts, which is basically the unwinding of the product rule in differential calculus. So so the rule says that integral of uv, of u and v being parts of the integral, let's say dt, whatever, that should be u times the integral of v minus the integral, dt, whatever. So u prime times integral of v with respect to v, respect to t. Okay, right, so then what we need to do now is find a useful substitution for u and v respectively. And what I can tell you is that in general what you're trying to do is get one of those to become 1, because then you're just making yourself, you're making progress that way. So what I'm going to do is choose u as t, because we know that t is going to differentiate to 1, which means that we can get ahead of this really kind of hairy expression. Okay, so then let's just say u should be t, and v is going to be that. Okay, fabulous. Okay, now we're going to do just substituting. I always do this. I just kind of work this out first and then integrate it in the next step. Okay, so then we have 1, and this is where I said u should preferably be a function which reduces to a more simplistic kind of form. when you differentiate it. Okay, so that's, and you know, this is basically the same thing as, well, using a constant rule, we know that that's equal to, oh, I forgot the minus here, shame. And we basically end up doing the same thing over again. You get an idea. So then that's equal to, I'm going to just save some time because I'm already kind of doing this in 10 minutes, which is appalling, considering those are two relatively easy Laplace transforms. Anyway, that's going to be 1 over s squared, because you know you're getting this negative. Wait, does it? Okay, yeah. Okay, so then, right, I'm just gonna do it again. You get and this, sorry, we know that this is equal to, okay, right, what we have here is you're going to have essentially minus ts, we're just going to rewrite it, e to the power of minus t, minus and then all we need to do is find the definite integral form of this. Right. Okay. So if we just look at if we just take the limit as a approaches infinity of minus t over s, yep. Okay, what we get is, okay, so here's where it gets a bit confusing, so pay attention to this. As t approaches infinity, the relationship is still going to be linear, because s is, you're just taking a number and dividing it by s, so it's not going to increase very, very quickly. On the other hand, we have an exponential function here, which means that if the t here approaches infinity, the overall convergence, not divergence, convergence, because it's going to approach 0, is going to be faster, because, that's how exponentials work. So then what we're going to get is, we're going to get an expression here, which equates to 0, because, as I mentioned before, this is going to approach 0 faster than this is going to approach infinity, or minus infinity. So then we have 0 minus, and here again we have a 0. There's no point in discussing it. It's 0 as well, because this is going to approach 0, and yeah, 0 minus 0, and then we're going to use the technique we mentioned here, definite integrals with the lower bound being 0. So then what we're going to do is evaluating when t equals 0. What we're going to get is, here it's going to be 0, and here it doesn't really matter what this function is going to be. Well, it would be. Well, it doesn't really matter, because we know that the product here is going to be equal to 0 by the fact that 1 for factors is 0. So let's just leave it here. And in the meantime, we know that e to the power of minus st, that's going to be, what is it going to be? E to the power of minus something s times 0. So you know that's basically about 0 equals 1. So yeah, we have 1 over s squared times 1. Yeah, that's where we're finishing up. And you know, plus 1 over s squared. And that's our answer. So you can say that Laplace transform of t, or essentially, well, some people write it like that. I don't like it. It's ugly, but okay. Okay. That's our two first Laplace transforms. And actually, we find something very interesting. You find that the more you increase this exponent, the more you increase the power of t, because you can view 1 as essentially t to the power of 0. Then you find out that, very interestingly, there's a pattern there with factorials, and I'm not gonna spoil it. I'm just gonna show you next video. Also, as I mentioned before, we're gonna try and solve a very difficult one, which is essentially sine of at. Not really that difficult, but it takes time, and to be honest, if this took me 17 minutes, I don't know how I'm going to manage to do it in a fair amount of time. Okay, so yeah, we'll leave it for today, and yeah.